All right, so let's talk method number 2. Method number 2 is, we're going to call it substitution method. The substitution method. Because of how we'll go about doing this one. All right, so let's say we've got, and the system will look slightly different, I guess. Make a point about that. 2x minus 3y equals 13, y equals minus 4x plus 5. Well, right off the bat, it's set up anyway a little different than the previous one, and I did that for a reason. Yeah, this one we are going to use solve by substitution. The other method, it's good to know both of these methods because it's sometimes the easier one than the other. Now, yeah, like I said, this one is really nicely set up for substitution because what I can do here is take this bottom equation, just talk about that for a second. This bottom equation is telling me y equals negative 4x plus 5. In other words, y is equivalent to negative 4x plus 5. Those things, in other words, are the same thing. Y and negative 4x plus 5. So one is as good as the other. All right, with that in mind, can't we then say, take this and substitute it for that if they're the same thing? That's what I'm going to do. I'm going to take this expression and substitute it for y back in the other equation. Hence the name substitution method. So if I do that, that top equation becomes what? 2x minus 3 times, though, not y. I'm going to replace the y by negative 4x plus 5. And that equals 13. Okay, so you see why we did that? Now, it's not a totally give me x equation, but it's an x equation now, isn't it? It's an equation that has only the x variable in it. I can solve for x. Just have to distribute a little bit. Distribute the negative 3. That'll be 2x plus 12x minus 15. See that? Negative 3 times negative 4 is positive 12x. And then negative 3 times 5 is negative 15. That equals 13. Now what? Like terms? 2x and 12x is 14x. 14x minus 15 equals 13. What's next? Add 15. Yeah? 14x equals 28. Divide by 14. X is 2. Which again is only half the answer. I still need the other half, the y. Now looking back at the equations, which does it look like is a good candidate to solve for y here? That second equation looks a whole lot easier than the first equation to solve for y if I know the x value, Sam. I know the x to be 2, so can I substitute the x to be 2 here? And I'm saying this is a lot easier than doing it here, isn't it? Because it's already got y equals. So just substitute the x to be 2. And there you go. Y would be negative 8 plus 5, so y would be negative 3. 2, negative 3. Works in both cases. And if you want to, quick check here. Check to make sure that works. If I do 2, negative 3, that would be 2 times 2. 2 here. Be 4. Negative 3 here, so that'll be negative 3 would be positive 9. Sure enough. 13 equals 13. Negative 3, 2. Pretty much already did that one, but yeah. There you go. Does work in both cases. Okay? Question or concern? Right. Okay, let me show you this one here with the substitution. We have to maybe do a little bit on this one, but not too much. 2x plus 3y equals 13 minus 4y plus x. That equals 1. Okay. I'm going to solve this one by substitution. However, I have a slight problem with doing this one by substitution. Not much too big of a deal, but there's not anything just quite yet I can do substitute right off the bat here. Because to substitute, I need an x equals, a y equals, or something like that. That's an easy, quick fix because what could I do here to get something I could use for a substitute? Move the 4y, yeah. I can solve this equation very easily for x, couldn't I, just by moving the 4y? So let's do that. Add 4y here to both sides. So I get x equals, let's say it's 4y plus 1. I can't combine those. Yeah, make that little quick adjustment. Now I have something that I can do for substitution here, can't I? What's this telling me right here? X is equivalent to 4y plus 1. So what can I do with this 4y plus 1? I can substitute the 4y plus 1 back in for x here, can't I? In this case, I'm substituting for x. So I take that back to the other equation for x. So that would be 2 times parentheses 4y plus 1, because that will have to be distributed, plus the 3y equals 13. Now I've got something I can solve, can't I? Distribute the 2, the 8y plus 2, plus the 3y equals 13. Like terms, I've got 11y there, plus the 2 equals 13, don't I? Right? Subtract 2. 11y equals 11, divide by 11. You got y equals 1. We done? It's half the answer. We need the x2. And again, this form of this equation would be real nice to find the x, wouldn't it? Just plug in the y to be 1 right there. X is 5. 5-1, solution? Question or concern? All right. Let me mention another one here, or two. Got that one? Okay. 4x minus 3y equals 8. 8x minus 6y equals 15. First point about this one to make is, when you come to one of these, it doesn't tell you which method to use. It's obviously your choice which method you want to use. Now this one, there's definitely one of the methods much easier than the other because the other one would probably involve some fractions. Which method probably on this one are we going to choose? Probably elimination, yeah. Because if you think about it, if I try to solve a variable, for any of the variables here, I'm going to get some fractions. So yeah, this one is probably much preferred method is the elimination method. So I need to eliminate one variable or the other. Which one? Actually, well, which one do you want to eliminate? Do the y's? Okay. Let's do the y's. That's a good one. That's a good choice. All right. Maybe not the easiest choice, but it does bring up a point. Why do it the easy way? All right. Yeah, so the LCMs, notice there, we could do 18, but 6 would be, or 12. But 6 would be the least common multiple because both of those have a multiple of 6 in them. All right. Now, the thing of this is I need one of them to be positive 6 and one of them to be negative 6. They're both negative. So how am I going to fix that? I need to multiply one of them by negative 2, don't I? Or multiply by, let's just do the top one, we're just going to do the top one, multiply it by a negative 2. That'll make that, cause that to be a positive 6. So if they're both negative, yeah, just change one of them to be a positive by multiplying by negative. All right, so that'd be negative 8x, the top, plus 6y equals negative 16. Then the bottom is just 8x minus 6y equals 15. Leave it all alone. Okay, yes, which brings up the next point I wanted to make on this. In this case, they both cancel, don't they? Hasn't happened on any of the ones previously, so let's talk about it. All right, so that's 0, so this side's 0, isn't it? This side's negative 1. Okay, we've talked about such things before, right? When we get this number equal number scenario, there's two things that can happen. You can either have no solution, or there's infinitely many. What is it in this case? No solution, yeah. If you get a contradiction here, something that doesn't make sense, that's a false statement there. Yeah, remember that's termed the no solution scenario. Okay. There's no solution to this one. You just can't get anything that would work in that. And it's called, the system's called an inconsistent system. You know, if it was just one, if it was just an equation, it's a contradiction, but if it's a system, it's inconsistent for obvious reasons, okay? So I'd ask about that's the title, I guess you might say, of the system, or what kind of system it is. No solution is the solutions, yeah. There is no solution. Trick question. Okay. All right. Now, I would say, you know, if you get the other one, where you get an always true statement, that one's called a dependent system. If you get an always true statement, that's called dependent system. I think they might have that phraseology in the problems there, so if I get 0 equals 0 or 5 equals 5, always true. This is called a dependent system. Okay? All right, now, let me show you this. There is a, actually, as far as the system goes, that's an easy one. Hopefully, anyway. Isn't it? If I try to solve that system, what do I have to do? Anything? What will eliminate right off the bat? The y's will eliminate. So this one's pretty cut and dry. Just add those two together. We get 2x. The y's eliminate equals 8. Divide by 2. Got x is 4. Then the y, well, the y value, just substitute x to be 4. I'm going to plug it into the second one. 4 plus y equals 6. All right. So what's the y? Y is 2. Okay, so 4, 2, solution. Now, what I was mentioning there is, let's think about the graph of these. If I graph x minus y equals 2, the first one, graph number 1, it's a line. Well, the x and y intercepts would be pretty easy, wouldn't they? If the y is 0, I get x equals 2, so I'd have 0, 2, 0. And if the x is 0, I'd have minus y equals 2, so that would be y is negative 2, so that's 0 and negative 2. Okay, so the graph looks like this. 2, 0, 0, negative 2. All right? So number 2 is the x plus y equals 6, also a line. So if I get the x-intercept and the y-intercept, the x-intercept, let y be 0, hey, that's x is 6, 6, 0. Be the x-intercept, then the y-intercept, set x to be 0, and that's y is 6. So we get 0, 6 also. Okay, let's look at that. 6, 0, and 0, 6. What we notice about these two lines is what? They intersect. And do you notice anything in particular about where they intersect? Hint, 4, 2. Okay? Check this out. All right. This intersection, yeah, even with mine not so accurate here, it looks pretty good. Okay? 4, 2 is where they intersect. That's not by coincidence that those two things are the same. This intersection point and this solution to the system, they're exactly the same. Yeah, it turns out, graphically speaking, the solutions to a system are where the graphs intersect. So, let me write that down. The solutions to a system are where the graph intersects. Or graphs intersect, I should say. The intersection points. Solutions are the intersection points. Which explains, right, why we're getting one solution. We're getting one xy on all these, because if you go back and look, all this equations that we did were linear. They were lines. X to the first, y to the first equations. All the ones we did. X to the first, y to the first. So the top one was a line, the bottom was a line in all cases that we did. How many times is a line going to intersect? 2 lines, I should say. How many times is 2 lines going to intersect? Yeah, if you've got 2 lines, they're going to intersect one place. Hence, that's why we're getting one solution for those systems. Now, if we have a different graph, we're not going to have these, but if I had a system where the graph was kind of a curve and then a line, how many solutions does that system have? That's going to have 2 solutions, yeah. So it's all dependent on how the shape of the graph works. If you have 2 cross where they cross twice, there's going to be 2 solutions to that system. Like I said, we're not going to do those, but you may have to in a later course. So, well, the reason you don't want, because sometimes you get fractions involved and it's hard to tell just by graphing maybe exactly where those are. So these are solving it this way, algebraically, if you want to say it that way, is much better, because sometimes if you have some graph paper, you get a little more accurate, but sometimes you get a little off, and so, but it is a good check for it. But now the other thing point I was going to make before we get back to our ticket problem is this. Yeah, lines intersect one place. However, there is an exception to lines intersecting in one point. Doesn't that explain back, it was a problem I had right here, right before we did this. I had no solution. Why were those lines, why did I have no solution? I can't remember why would we have a no solution? They don't intersect. They're parallel, yeah. Those lines are running parallel. Mm-hmm. If the lines run parallel, they're not going to intersect, or some other scenario, but yeah, no solution means their graphs don't intersect.